Today's session is about synchronous reluctance motors and their capabilities, notably in terms of energy efficiency levels that can be reached. This is a magnet-free technology that can reach IE5 efficiency levels as much as permanent magnet technology. And then the webinar will also explore the potential for upgrading existing IE3 induction motors with synchronous rotor and then to reach higher efficiency levels. Our speaker today is Bojan Jakovljević, project manager at Končar motor manufacturer. So now, Bojan, you can go ahead. The floor is yours. Thank you.
Thank you very much for this introduction. I will share my presentation now. So, as Fernando said, main topic for this presentation is our synchronous reluctance motor, which can reach the IE5 efficiency levels, same as any other motor with permanent magnet. Since I'm a project and electrotechnology manager in a company which produces electric motors, I will mostly deal with some technical aspects of these motors, compare them to other technologies. Also, some topics of these presentations are also current efficiency requirements. We will also take some financial aspects of these motors. Are they good investments? And at the end, we will show some, real data regarding technology test with motor with asynchronous aluminum rotor versus the synchronous reluctance motors. So we have some real measurements. Also, of this presentation, I always try to back it up with real data, so not with technical data, not just with some marketing data or something like that. So I really hope that this presentation will be really useful to you all. So, as I said, first topic will be efficiency requirements, mainly for the European Union market. So today we know, I think that everyone who is dealing with electric motors, purchasing electric motors, producing electric motors on the European market knows that actual current regulation, which is in force, requires IE4 motors at as maximum efficiency levels required for the power range from 75 to 200 kilowatts for 2, 4, and 6 poles. This is basically in force 2 years now. And today's presentation is talking about IE5 motors. Probably some of you will ask why we need IE5 motors. Regulation is requiring only IE4 motors. Well, the reason is, I would say, really simple, and that is the saving of the electrical energy. And through the savings of electrical energy, we will also save money. Our products will be more, competitive on the actual regulation. So in order to, let's say, save this money or become more competitive, we shall see in more detail our IE5 motors actually a good investment. So as we can see here, main part of cost of ownership, which is consisted of purchasing of this motor, installation of this motor, maintenance, and energy consumption. The main part for the total cost of ownership for total lifetime of motor is actually energy consumption. And main reason for this because electric motor is quite a robust component. And this quite robust component can last 15, 20, even 25 years without any problems with regular maintenance. So over the lifespan of the motor, 25 years, huge amount of energy will be consumed. So first part here is to see what we can reduce in this graph, and that is, of course, energy consumption. We can reduce this energy consumption simply by going with replacing our old motors, because at the moment in industry there is a lot of old motors here. There was one really good project, EUMOR, which actually has the exact numbers for how much of these old motors is currently in the market. So if we replace those old motors with new motors, we can reduce this energy consumption and have more competitive production. So this is the main goal, and this can be achieved, of course, with high efficiency IE4 or IE5 electric motors. So in order to get the electric motor, we need to purchase this electric motor. And here is some return on investment, which actually targets only motor purchase of the motor. This is based for the 15 kilowatt motor, 4-pole motor, which works 4,000 hours per year. This means 2 shifts per day. So this is investment return for only motor, so without variable speed drive. So this is return for this motor in 1 year and 6 months approximately. So basically this is if we change our old motor, because as I said, most of the production today in all the production facilities are using old motors. Rarely there are IE3 motors, maybe only the new machines, new equipment and so on. But mostly we still can see huge number of the old motors. So VSD is not included in this calculation, but so basically we need to do much more detailed calculation. This can be, let's say, for if we replace old IE1 motor induction asynchronous motor with IE5 induction asynchronous motor. But this motor will be quite large, maybe too powerful for some of the applications. So, and we know that IE5 motors, they are usually on today's market available only in synchronous versions, synchronous reluctance without magnets or permanent magnet electric motor. So to go into more depth, we have here a complete system efficiency calculation. And we can take into our calculation as well the price of the variable speed drive. So this variable speed drive, of course, this is electrical component. Every component has its efficiency. It cannot be 100% efficient. Even it is, I must say that variable speed drives, they are really, really close to the ideal, to the ideal efficiency level. So we see that motor efficiency is 95.1% for 515 kilowatts motors, 4 poles, and drive efficiency 97.6%, but total efficiency, total system efficiency is 93.3%. So this is something as well which we need to take into our calculation of the total cost of ownership, return on investment, and of course energy savings. So this classification, it is determined with the load of 100% and 90% of speed. So, okay, we know that induction motors, let's say 1500 is synchronous speed, but asynchronous motors, they will not run on this speed. They will run on speed which is below this synchronous speed. So synchronous motors, they will run with this synchronous speed, but when we reduce their operating point, their frequency, they will be near this speed of our old induction motors. So this is one of the reasons why there is operating point in the 90% of the speed with the synchronous motor with variable speed drive. And IE1 asynchronous motor is basically on the same speed due to slippage of the rotor behind of the synchronous speed. So we can see that our return on investment is really increased, but we took into calculation here basically state-of-the-art variable speed drive with all the components, equipment. So not cheap equipment, but in real applications, this number of the years which is needed to return this investment can be only low. So I have here some comparison. It is used for 25-year lifespan of the lifetime of the electric motor. So we can see that IE1 motor, direct online, motor has efficiency 88%, IE5 with VSD, as we see as we saw from the last slide, is 93.3%. So we have return on investment 5 years, 10 months. We can say 60 euros a year. But if we have this year one direct online motor, we can replace it with IE4 direct online motor. These IE4 direct online motors can be found on today's market. Because why? Because of the regulation. We saw on the first slide that regulation is pushing this to the IE4 motors. And most of these IE4 motors on the market actually are induction asynchronous motors, because this is the most common motor in the industry. There is a lot of knowledge about this motor in the general industry. So this is basically pushed from market to go into this direction. So you can find the IE4 direct online motor without any problems on the European market for your application. So they are ready to use. You can see that efficiency is basically higher than with the variable speed drive and the IE5 combination. So we have savings around 700 euros yearly, and return on investment is of course faster. But one thing should be considered here. When you have the old motor, this old motor is probably not loaded with 100% of the load, its rated load. It can be 75%, 50% loaded, on even less, 20% loaded. Because in the past, all these old motors are quite too big for the applications. They were used just for safety. So if you use variable speed drive in theory should optimize this, complete unit. If this old motor is direct online, it is probably not loaded with 100%, and it probably does not have 88.7 efficiency, but even lower efficiency. So when you use now, let's say, IE5 motor with variable speed drive, this variable speed drive should optimize this working point. So this depends from case to case. This depends from case to case, but you can have return on investment theoretically even lower than these 5 years, 10 months. It can be even probably the same. It depends on the actual drive system you have in your application. So it can be taken step by step. These calculations can be made. It is not a problem. So you can see your real data. This is example for 100%, as you said, rated load, and 90% of the speed for IE5 synchronous motor. And when we have old IE1 motor with variable speed drive, if you replace it with IE5 variable speed drive motor, we can see that in this case, we have the biggest savings, 800 euros, because as I said, variable speed drive, we also get some of the losses, and old variable speed drive should be replaced with new ones as well, because the situation is the same. New drives also have regulatives which require them to have high efficiency levels and low losses. So this basically, I would say, as a rule of thumb, if you have old motor with variable speed drive, it can be replaced with IE5 motor and variable speed drive. If your old motor is direct online and you do not see any potential savings with the frequency inverter, or you are not able to put the frequency inverter in your operation, then you can go with IE4 direct online motor. Those motors are available on market, so you will get basically in all these three cases more or less the same yearly savings. Only return on investment can be different, but when we take into consideration of the 25 years lifespan or 20 years lifespan of the motors, these are not so big, quite big numbers. But in any case, I will say that this purchase is justified of the motor, and that also we have covered another thing, which is cost of running. We will save in total energy during the lifetime of the motor. As I said, variable speed drive, you can get some benefit. Yes, it will increase your return on investment, but it can reduce your cost of running if you have a heavily partially loaded system. Also, you can reduce the maintenance operations, because variable speed drive is good starting point for cost-effective predictive maintenance. You can connect the sensors to it, you can get yourself some SCADA data, you can get early warnings, so you can do the maintenance operations of the motor only when it is truly needed. Not, let's say, every year, maybe every 2 years or something like that, depending on the motor operations, motor work hours, etc. So this can get further benefits with improved power factor, less reactive power, and so on. It is additional component needed, but this additional component have its benefits as well. So this should be taken everything into consideration. Another thing which brings reduced downtime for these kind of motors is basically efficiency level. We can see here that temperature rise of the, let's say, winding and so on, the winding will just drop from EA1 to EA3 to EA5. This is temperature rise of the winding for 20 kelvins for IE5 motor. So if we have, let's say, 25 degrees Celsius, motor's winding will be on the 45 degrees Celsius, and the winding isolation can withstand 155 degrees Celsius. So you have huge margins regarding the temperature, so this winding can work forever, definitely forever. The similar thing is with the bearings as well. For the IE4 and the IE5 motors, you can see this dramatical drop of the temperature rises of the bearings as well. I mean, the bearings should be replaced if they are loaded with some, in this case, with really low temperature, with some low how to say, forces. They can even withstand 100,000 working hours without any problems. But in any case, we would like to replace them in the regular intervals, just because same as oil in your car, because the oil is chemical component, and same is with the grease of the bearings. It will degrade just because of the time. You can have motor which is not working at all, but you will need to replace these bearings. But in any case, you will reduce the downtime as well. So I think that with this cost of knowledge, we covered everything. Purchase, yes, it is justified. The investment will return itself for 4 or 5 years. Cost of running, yes, cost of running will be reduced because energy consumption will be reduced. Cost of not running, you will increase the maintenance intervals, you will save money on this maintenance operation, so total cost of ownership will decrease. So as a conclusion, IE5 motors, I think they are, or IE4 motors are good investments. Another thing, if you want to replace one motor, this is the main thing. You have your machine which is doing some operation in your production. If you want to replace this machine, this motor's machine, you are of course aiming for the same motor dimensions. With IE5 synchronous motors, dimensions will be the same. It will be the same. No problems there. Also, you would like to have maintenance tasks, parts, and everything else. So let's say bearing size. You want them to be the same. You do not want some special tools. This is again possible with synchronous motors, but mainly with synchronous reluctance motors, because they do not have magnets, which can, and this can be proven quite difficult to maintain those motors. And also another big part which should be considered is, can you integrate variable speed drive in your current process? If not, if you cannot change electrical installation, if your process doesn't, I mean, you do not see any benefit. There are benefits, but if you do not want to invest in this part and do not see any larger benefits, then in this case you can choose IE4 induction motor, which are as well more or less in the same dimensions, with same dimensions. Maybe the length of the housing is bigger, but they will have all the main dimensions the same. So this means they are using more better materials in the rotor, as the copper casted rotor instead of aluminum, a grade of the magnetic material is better, and so on. But they can be in the same dimensions, so you can replace your old motor with this new one. So, as we already said, example of replacement scenarios: if you have your one motor with variable speed drive, you can replace it with IE5 motor with variable speed drive. IE1 asynchronous motor direct online. If it is possible, you will probably integrate variable speed drive. If not, you can go with the IE4 motor direct online. In both cases, you will get the yearly savings. I mean, yearly savings, they are in the range of 600 to 800 euros for this case of the 15 kilowatt motor. But this, what if you have 100 motors in your production? So this will be, let's say, 700 euros times 100. So this number can be really huge if there is a huge amount of motors in the production, or if you have some pump station which is working 24/7. So that really makes sense to replace this old motor with new ones, and these numbers will change to the better, not to the worse. So return on investment will be even faster. So while I'm talking with these IE5 motors and variable speed drive, because it is not possible to have in today's market, what is offering on the market for IE5 motors, those are mostly synchronous reluctance motor and permanent magnets motors. But both motors require variable speed drive. So this should be taken into consideration while replacing the old motors. So now we know that IE5 motors are good to go with this investment. We will see now, is it possible to use motor with magnets or without magnets? Here we have one comparison of potential motor technologies. Here we are using this just to compare. For IE5, yes, we can produce IE5 induction motor without any problems, but my disadvantage will be, because this motor will be one ISC size or two ISC sizes bigger, then it will be more heavier, can be integrated into our actual system and so on, but it can be produced. This motor has its benefits. You do not need variable speed drive. You can put it direct online, it will work. With synchronous reluctance, main advantage is it is a really efficient motor for a low material cost, but it will require some advanced control algorithms. But today, more and more variable speed drive manufacturers are able to drive synchronous reluctance motors without problems, and actually those algorithms are quite advanced, so there will be no problems whatsoever in controlling these motors. With permanent magnets motors, they can be really light motors. They are really light motors because you have magnets. They can be maybe even one IC frame size smaller, but you have those magnets which are actually critical component. They do not have such a big resistance to high temperatures. You can get a complete demagnetization of these magnets. You can get maybe partial demagnetization. So you will probably have more problems in these high temperature applications. You can have problems with raw materials, manufacturing, and so on. So basically, this synchronous reluctance motor, it can be, how to say, maybe the best option of these three possible technology. So it is basically in the middle, and we can see this by these dots. Also, this is not an error for the induction motor resistance to high temperature, because when we have IE5 motor, let's say induction motor, it is huge motor. Because it is huge motor with such a high efficiency, its winding will be really, really cold. So it will have a really good resistance to this high temperature. But what is the cost? The cost is a really huge amount of materials, which you do not need with synchronous reluctance motor. And with synchronous reluctance motor, you do not have any additional equipment, additional elements. So this can be maybe the best step for this IE5 technology. So why, as I said, why is the type of material used for efficiency important? Rare earth, magnets, and so on, they are quite critical in many aspects. You can have potential problems with supply chain. As well, there is upcoming regulatory review in the European Union, which will actually take into consideration what amount of materials is some motor using to achieve this efficiency. So it is not the same if the motor is using, it will not be the same if the motor is using some critical elements recognized by the same regulators, and if you do not use those elements to achieve IE5, same basically efficiency rating. So there, synchronous reluctance motor is not using any critical elements. So this type of motor for IE5 efficiency will comply without any problems with upcoming eco design regulations. So this is another plus, I will say, for this type of motor compared to another IE5 motors. And also you can stay in the same ISC size, same as you have your actual i3 motors. So no additional materials will be used. And the return of investment can be still quite short. So these are some, this is not my slide left, these are actual notes from the regulator. So you can see here, wide range of requirements will be considered, energy efficiency and resource efficiency. So how much resources are we using to get this, to achieve this IE5 efficiency? Product durability, reusability, and so on. Presence of substances that inhibit circularity, recycled content, and so on. So when we put all these points into exactly these points into comparison for each motor, we can see that energy efficiency and resource efficiency for induction motor, you will probably need, let's say, big motor. It is possible to achieve it. You will need a bigger motor and so on, but none of this material will be critical. It can be recycled at the end. So all in all, it is not such a big problem. With synchronous reluctance motor, you can stay in the same size. With synchronous motor permanent magnet, yes, it can be maybe one is IC size is smaller, but it will use some critical components and elements. Repairability, motors with magnets. First of all, when you disassemble bearing shields, you need to pull out this rotor, and this is usually not an easy task because the magnets, of course, will stick to the stator of the motor. You will probably need some additional tools in order to put this rotor out of this stator. Then if you put this rotor near the metallic objects, metallic fillings, they will all stick to this rotor because this rotor is with magnets. So all in all, you will need a special, how to say, room for maintenance of these motors. This cannot be probably done in your regular maintenance, which all the companies have. So this must be even simple bearing replacement. You will need to take more care and more money to service this motor. Yes, you have as well circularity and recycling. It when you have the magnets inside the motor and you want to recycle it, they will stick to all elements, all the components in this recycling plant. So I know that they do not really like these types of motors because they can produce a lot of problems during the recycling and so on. So as you can see here, one of the drawbacks for these IE5 motors is that we need variable speed drive. So this variable speed drive also requires some resources to be manufactured. So this is something as well which probably I think that further regulatives should take into consideration, because this is another component which you need to take into account and compare it with, let's say, induction motors. So here we can see that synchronous reluctance motor probably will be future-proof for the new regulations, but everything is still in progress, so we will see what the future will bring to us. So let's see a brief technical details of these synchronous reluctance motors. We saw that IE5 motors, yes, they will bring savings. I think that IE5 synchronous reluctance motor, it is future-proof regarding any future regulatives for the European Union. So this is motor to go for the IE5 efficiency level. At this point, if we cannot use IE5 motors and ergo speed drive, we can use IE4 motors and in asynchronous technology. So, brief technical details. Why is this? What is the difference between the synchronous reluctance motor and asynchronous motor? Basically, you have the same type of starter, same housing, terminal block, same production procedures and tools. So, if you produce asynchronous motors, stators, you will definitely be able to produce synchronous reluctance motors without any problem by using your existing components, tools, machines, and so on. The main and only difference is that in the design of the rotor, there will be needed some extra work in order to make the stacking of this rotor sheets, magnetic sheets on the motor shaft. So this is basically the only difference in the terms of production of such motors compared to induction motors, asynchronous motors. So you can see basically the all maintenance operations will be the same as well. So without any problems, we can use synchronous reluctance motor in IE5 technology with the same maintenance procedures and with same production tools. So brief principle of operation. We can see here at bottom left, we have one picture. This is basically, let's say, stator of the motor, north pole and south pole of the motor. This motor have this north and south pole, they produce their magnetic field. This magnetic field will not go through the air, only small amount will go through the air. Of course, the magnetic field would like to go only through the iron. Or what we can say, it will go to the path of the least magnetic resistance of the magnetic reluctance. So what will happen on this first bottom left picture if we do nothing? Of course, if we just put it like that, there is no load on this rotor. This rotor will basically align itself. One pole will be beneath the north magnetic pole, another part will be beneath south magnetic pole. So it will align itself to the lowest, least part of magnetic resistance, basically to reduce its magnetic potential energy. So then if we rotate these north and south poles, this metal part will follow this north and south magnetic pole. So basically we can rotate, if we can rotate this rotor, that is basically the same thing which will happen in the electric motor. We have the sheets of iron which will be put into the rotor of the motor. D-axis is the axis with the low reluctance part, and Q-axis is the axis with the high reluctance part. So there will be not a lot of magnetic field going through this air. So if we have rotating magnetic field, this magnetic field will basically pull this rotor together with itself, and the complete system will rotate. So basically two things you can use. Here we can say that the magnetic lines, they would like to reduce their length. And on this left picture, we can see they are skewed, but they do not want to be skewed. They have the tendency to be straight lines. So this is the force which is happening and which is transferring basically from the stator to the rotor, and which will make this complete system to rotate. Of course, I tried to explain this in the fastest possible way, but this theory behind this is actually quite complex. But I hope that I managed. And why is this synchronous reluctant motor so efficient? Well, basically, no rotor bars as in induction motor through which some current passes. If we have current which passes through the rotor, we know that we have losses. In synchronous motors, we do not have any losses in the rotor, and which means that we will eliminate all these resistive rotor losses. So these additional savings are actually pushing this motor in IE4, IE5 efficiency levels without any problems. We do not have any heating on the rotor, so complete system will be much colder, much longer lifespan, and so on. So this is the main reason why these motors are so efficient. Also, the rotor is rotating with the same speed as the stator magnetic field, which means there are no eddy currents, not so much eddy currents in the rotor core. Of course, there are some, but not so much as with the induction motor. So we have here basically more or less as a rule of thumb, we can say losses are zero in the rotor, we can completely eliminate them. And this is the part which brings good efficiency to those motors. Main uses, and here are only some usage scenarios. Induction motor, high efficiency, IE4, let's say induction motor, they can be used basically in all loads with extremely dynamic load changes. So if you have some big winch on the motor, and if this winch usually gets stuck, so you need this motor to produce really huge torque in any time, basically instantly, then you will probably go with the induction motor in this case. It is not impossible to use even synchronous reluctance motor, permanent magnet motor for this application as well. As I said earlier, these control algorithms from the variable speed rise are quite good in today's operations, even in these marine applications. So it is this what is written in this table. It is not absolute, how to say, limit for the synchronous motor, not for permanent motor, not for induction motor. So they all in all, they can cover all of these application, but these are the most common applications in today's market and today's market. So I have shown two examples of synchronous reluctant application which can be used with this technology and not, let's say, with permanent magnet technology. Only one is here. This is explosion-proof motors. You can have explosion-proof motor IE5 efficiency level in explosion-proof design. Why is that? Because you do not have additional component which can cause problems, let's say with magnets. You can have a demagnetization of these magnets, and what will happen to this motor? It will not operate on same temperatures as before. And this is not acceptable, let's say, for these explosion-proof motors. With synchronous reluctance motor, you do not have magnets, you do not have this additional component. There is not possible to have any other problem basically than from the winding of the motor bearings, which can produce excessive heat. But if a winding is producing excessive heat by itself, it is probably due to overloading of this motor, not just because it has some short spike of temperature inside and everything is then cooled down again. So, and another thing, if you have overspeed of your rotor in the motor with magnets, there can be some huge voltages induced, which can produce maybe sparks, something like that. And this is as well not acceptable for some of the explosion-proof applications. Another thing where we can find a good application for this synchronous reluctance motor is basically fan application, heating, ventilation, air conditioning, because by itself, heating and ventilation and this air conditioning can be much more efficient if you use variable speed drive for its application, which also can be shown on the further slide. Here, this is the real data. As I said, I would like always to give as much as possible the real data for this application, not just on marketing values. So we have here with blue lines, on the blue it is marked, let's say, all the design of the fan, and the green one is the synchronous reluctance motor in combination with integrated variable speed drive. We can see that both the input power, this is input power, so this takes into consideration both motor and variable speed drive losses. But we can see that power consumption is dramatically reduced, as well as the rated current. So to the network, to the grid, we have a good efficiency, a good, how to say, reduced current, even though we saw earlier that when we compare these two technologies, synchronous reluctance motors tend to have the highest rated current compared to permanent magnet motors or compared to the induction motors. So we have here, in any case, reduction of this current towards the grid, because the variable speed drive will actually do this compensation of energy, a partial compensation of energy. So your power factor will increase, and in the same time, current, which is taken from the grid, will reduce. So this variable speed drive will even give smaller current from the pull from the network. And why are those fans a good option? Because this is, let's say, for transformer cooling application, it is not always loaded by 100%. So if it is not loaded by 100%, you do not need 100% of cooling airflow. You can reduce this cooling airflow by reducing the speed of the motor without any problem. So this will bring additional energy savings. So what else we can do? Let's say we have briefly new i3 motors. You do not want to, let's say, replace your briefly new induction motor. As we spoke earlier, we try to replace old motors with new ones to save energy. But i3 motor, it is quite a good motor. You already invested money. Maybe it is even not paid off still, but if you want to have the further savings, this is some alternative to purchasing a completely new motor. You can, during the regular maintenance operation, you can remove this aluminum rotor from the motor, and put, instead of this rotor, you can put synchronous reluctance rotor with the same design in the terms of length of the rotor and in the term of the diameter of the rotor. You can put the new bearings on this rotor, and basically you will get the synchronous reluctance motor. But it is not let's just replace the rotor, and that will definitely have good operation, good work points, and so on. You really need to take care, because you can get yourself into the overmodulation part. This can be seen on this image to the right, where this switching stops in the warm point. That is because in this part, variable speed drive, it really wants to increase this voltage to get this motor to the most optimum point. Not all variable speed drives are able to work and to operate synchronous reluctance motor in this point. So this is something where you should really need to be cautious, because simply replacing of the rotor maybe will not give you the good results. So this should be done in the cooperation with the motor manufacturer. So efficiency in this case will definitely improve. It may not reach IE5 rating, it may just go from i3 to IE5, but in this case you will get more savings of energy than your relatively new i3 motor. Your only investment is basically to get a new rotor. You already, when you're doing the regular maintenance, you need to disassemble the motor and so on. You need to assemble it again. So basically work part of this upgrade can be eliminated, because in any case you will do it. So the old aluminum shaft and everything can be recycled. So this is something which we basically done. We have a i3 motor, which is not so old motor. So this is the reason where I said when we compare the two technologies of this motor. This is interesting. Why? Because the stator is the same. So we did not change the winding in this comparison. Upgraded is the motor with 3 kilowatts. of the power, so it was IE3 motor. Then we put the synchronous reluctance rotor in this motor. What we expected actually is to have voltage a bit higher, but voltage is left to 390 volts, which is really close to 400 volts, which is the input of the variable speed drive. And the motor efficiency is basically, in this case, IE4, and it is really IE4. It is 19.4%, and we have now 91.26%. So basically, this is the same motor, same stator, same fan. Everything is the same. Only the rotor is changed. So this is IE4 without taking into consideration variable speed drive losses, but if you already have IE3 motor with variable speed drive, you will definitely have a good return on investment in these parts, because this motor is upgraded basically. Of course, as we already said, synchronous reluctance motors, they have a higher rated current than the induction motor, so we have this increase of the current here. It is needed because you need to create this magnetic field, which we talked about earlier, which will basically go through these barriers. So we have a more magnetizing current, which will increase your total current. And that is another reason why we have a lower power factor. But at the end, this will be compensated on the part of the variable speed drive. Also, we see the temperature rise is significantly going down. So we have increased, how to say, bearing lifetime and so on. Another thing you could do in this case is, of course, to replace this aluminum rotor 4-pole motor with copper rotor. Again, you will get a really good efficiency. You will get an increase of the efficiency. All other parts of your electrical installation can be the same, because you are going to use, you will still have asynchronous motor, but now you will use a copper rotor instead of aluminum rotor, and this will bring you a lot of efficiency in level increase and energy savings, and this can pay back quite fast. But as I said, if this will be done with in the coordination with the motor manufacturer, because you will need some extra data to see if this is viable and if this is going to bring you enough efficiency increase. But I can say that yes, definitely it will bring. So for some conclusions, yes, IE5 synchronous reluctance motor, they are great investment. They will have short return of this investment, even though the current regulation does not require IE5 motors. All in all, I would say that if you have old motor with variable speed drive, yes, you should go in the direction to replace both old variable speed drive and this old motor with IE5 motor and new variable speed drive. We can have synchronous reluctance technology in IE5 ratings by using rotors designed without magnets. For IE5, also you will probably need to increase the quality of magnet of the iron, so that it have less losses per kilogram than compared to IE3 motor, but everything will still same in the same IC size. Another thing for synchronous reluctance motor, they are basically, I would say, future-proof regarding the new regulatives and so on, and your maintenance operations will be the same. This is for old motors, and for IE3 other motors, it is possible to, which are all new motors, it is possible to upgrade those motors by using synchronous reluctance rotor or copper rotor. So, thank you very much.